Okay, so a few items before we go ahead and get started. We are going to continue the happy minutes all through this week, all through next week. The only days we're not going to go ahead and do them is if we have a major exam, like on Thursday of next week. The 15th of next week, that Thursday, is when you'll have your first exam. That's going to be right before we get out for the Thanksgiving holidays. So more than likely on that 16th, we'll probably just pass those back, talk about any questions you may have, and we'll kind of see where we are at that point. Hopefully, we'll be pretty much done with graphing all the trig functions, but we'll kind of see and play it by ear. This Thursday, you're going to have a quiz over this material, not the trig functions, graphing them, but I'm talking about the homework we just turned in, law of sines and law of cosines. All right, so I've just given you two word problems. If you're very familiar with law of sines and cosines, should not be too difficult for you. We'll do that on Thursday, and then we'll just continue to work and see how far we get before the break. Does anybody have any questions? All right, now the happy minutes, if you are wanting to retake those, you can come in, just let me know which one you want to take. But let's go ahead and say that for every happy minutes we do, you have a week after that to do it. So like this one here, it's a Monday, so you have until next Monday to go ahead and get it done. And then tomorrow, Tuesday, you'll have until next Tuesday to go ahead and get that done. And we'll just keep going like that. Give you a week each time for those. Okay, so let's start talking about the graphs of sine and cosine. Now, these guys are going to be really, really important for you because the way we're going to go ahead and graph tangent, cotangent, secant, and cosecant is based off these graphs here. So we need to be really, really comfortable with these. And, I really hate to use the term memorize, but if you're not really comfortable with it, then maybe we just need to go ahead and memorize everything there is about sine and cosine. The more familiar you are with these two graphs, the easier the other section is going to be for you. Okay? So you will struggle a little bit if you don't know these graphs. Well, let's see what it says. The graphs of sine and cosine functions are periodic. This means that the function values will repeat as x increases. The sine value of the function is equal to what? The y value, just like we've been talking about. Every time we evaluate trig functions on the unit circle, we've been saying that sine is your y value, okay, at that corresponding point or angle on the unit circle. Also, the cosine value is equal to the x value on that point or angle on the unit circle. And then for the other trig functions, it was using some kind of ratio between either x, y, or even using the radius itself. Okay, so since the graph will complete one full cycle in the interval of 0 to pi, the period of y equals sine of x is 2 pi. So for this one, I'm going to go ahead and start by just giving you the graph of sine, and then we're going to kind of take a step back and figure out why do we have this particular graph to begin with. Okay, now sine is going to start at the origin. Okay, so we're going to have an intercept right here, an x-intercept at 0, 0. Then we're going to have a critical point at pi over 2, 1. We're going to have another 0 at pi. Then we're going to have a minimum. In fact, our first minimum at 3 pi over 2, it's going to be negative 1. And then we're going to get all the way back around to 2 pi. Okay, it's going to complete one full cycle in 2 pi radians. That's the number of radians needed for the graph to complete itself before it's going to repeat again. So sine, remember we're talking about the parent, is going to look something like this. Okay. So I'm going to see that exact same curve in the next 2 pi radians, and then the next, and then the next. So I'm going to see it come up, down, just like that. And then the graph is just going to repeat. Now it can also repeat in the other direction. So I'm going to go right through here like that. There you go. It's just going to keep repeating itself over and over and over again. Now, as we transform these functions, as I shift it horizontally, as I dilate it, reflect it, all that good stuff, the period could conceivably change. But let's kind of focus on just one period for this function here. Okay. Let's talk about these points first. Now, these are your critical points that you're really wanting to take a look at for every cycle, every period. We start with a 0, okay, because this is a x-intercept. Then we have our first maximum. Then we have another 0. Then we have our first minimum. And then we have our 0 again. our x-intercept. Okay. Now, I'm going to go ahead and mention it at the top of the lesson today, but you really want to be looking for these critical points every time you're going to go ahead and sketch a period of one of these graphs. Now, between these points, and it may not mean a whole lot to you today, but it definitely will when we start looking at these transformations, the horizontal distance between these critical points is always going to be the same. You should always be able to divide your period up into 4 congruent segments based on where these points are going to be. Going from 1, 0 to a maximum, 0, minimum, and then back to a 0 again. All 4 of those are going to be congruent. Okay. Any questions on that? Okay. Well, let's go ahead and identify these points right here. So this one right here at the origin, well, that's definitely 0, 0. That's easy enough. What are the coordinates of this maximum right here? There you go. So the x value, the horizontal, it occurs at pi over 2, but the maximum is 1. So we have the ordered pair pi over 2, 1. Okay, what's the ordered pair of the next 0? Where does that occur? It occurs at pi. So this one would be pi 0. And then the minimum, that would be 3 pi over 2. And then negative 1. Now remember, when we're talking about the maximum and the minimum, we're referring specifically to the y value in that particular ordered pair. The largest or the smallest element in the range. The x value is simply where it occurs. So we have our first max at 1 occurring at pi over 2. We have our first minimum of negative 1 occurring at 3 pi over 2. And what's the coordinate right here for the last 0 before it starts to repeat again? Yeah, it would just be 2 pi, comma 0. Now remember, this first paragraph up here is crucial to understanding why the sine graph looks the way it does. Remember, the sine value is equal to what? The y value of the ordered pair, right? So why don't we go ahead and take a look at a unit circle. Let's go ahead and compare this graph to what we've been working with for quite a while now. Let's go ahead and run through the same values. I'm going to start with sine of 0. So let's say I want to know the value of this function's sine at 0 radians. So that means I'm focused on this ordered pair. Well, what's the y value? 0. Okay. Well, think about what we're doing. We're inputting a value of x, and we're getting a value of y out of it because we're wanting to graph this guy. So we end up with the ordered pair 0, 0. And now let's just go around the unit circle in increments of pi over 2. Let's go next to sine of pi over 2. Okay. Well, at sine of pi over 2, what's the y value? 1. So I input pi over 2 to get out a 1. So I have the ordered pair pi over 2, 1. Is anybody starting to see where these are coming from? Okay. It's the value of the sine function as I go around the unit circle. Let's go to pi next. Okay, what's sine of pi? The y value at this ordered pair is what? 0. So what ordered pair would that provide me? Pi 0. You'll notice these are the exact ordered pairs that are creating my sine wave, that sine function. So if we were to continue with this, sine of 3 pi over 2 would give me negative 1. See, that was the first minimum that we had on our graph. 3 pi over 2, negative 1. And then we finished up, we got all the way back around to sine of 2 pi, which just gave me 0 again. So I had 2 pi 0. Okay. So that's where those ordered pairs are coming from. So if I were to go ahead and choose any radian measure, like let's say, if I were to choose sine of 45 degrees or sine of pi over 4, I'd be looking for the y value, right? The square root of 2 over 2. Well, I would still be able to locate that ordered pair. Here's pi over 4. So this one right here should be equivalent to the square root of 2 over 2. I'm taking the exact values just right off the unit circle. In fact, imagine if I had the unit circle in my hand, it were something tangible. What if I just snapped it right at this location right here and I just unraveled it? This would be providing me the graphs that I'm going to be looking at. Now, here's my question. Is everybody okay where these 5 points came from now? Why we specifically have them? Okay. Well, why is it going to repeat the exact same curve just over and over and over again? What's happening? That's exactly right. Say that a little louder, man. Aiden says coterminal. Because how many times can I rotate around the unit circle? A lot. I can rotate an infinite number of times, right? So see here, as soon as I get back around to 2 pi, well, these values are just going to start repeating themselves again. You already saw when I got back around to 2 pi, I got the 0. In fact, you saw on your quadrantal happy minutes today 5 pi over 2. If I went to the very next increment of pi over 2, I'm right back around to 1 again, which is where the next maximum is going to occur. So does it make sense, one, why it has a period of 2 pi? Because once you go past 1 revolution, the values start to repeat. Just like she said, they're coterminal. Now, the reason it goes forever is because I could rotate forever and ever and ever. I could continue to go as many times as I wanted to. Now, I'm going counterclockwise here, but could I rotate clockwise? Yeah, which is what's giving me the same cycle going in the other direction. Okay, good. All right, well, now that we have the graph of sine, we kind of have an idea where he's coming from, let's go ahead and talk about some characteristics. If I could rotate clockwise or counterclockwise an infinite number of times, well, what would his domain be? Okay, what's that, Stephanie? It would be all reals, yeah. So negative to positive infinity. Okay, what's his range? Let's see, how tall is he? Yeah, his maximum is 1, minimum is -1, so he can only exist between those values. Okay, and they are included, so -1 to 1. All right. Now, let's talk about the x-intercepts, but let's think about this for a second. The x-intercepts, just like the maximums, just like the minimums, how many of those am I going to have? If this guy's going to go forever in both directions, don't I have an infinite number of intercepts? An infinite number of maximums, an infinite number of minimums. So here's the thing, I don't want to go ahead and just say, all right, I have the origin as an intercept, because that's not the only one. I need to come up with an expression that's going to identify for me any of the infinite number of intercepts that I have. So your first intercept is at 0. Your next intercept is at pi, then 2 pi. Then what do you think the next one would be? 3 pi, 4 pi, and it's going to continue. What if you were to go clockwise? -pi, -2 pi. So basically I'm looking for a what? N pi, okay. Now, we can use any variable you like. So you want to go ahead and use n. Oops, I went to the wrong one. So let's go ahead and say pi n. For the earlier classes, I was using k, but the variable itself does not matter as long as you go ahead and identify what it is. We're going to have to say that n is an integer. Now, does everybody remember what the set of integers looks like? Or do I need to go ahead and write that set out real quick? Okay, well, it's the whole numbers. They're negatives, they're opposites, and what? 0. Okay, so I'll go ahead and write it out anyway. Why not? So the integers are going to be -2, -1, 0, 1, 2, ... Okay. So if you think about it, if you go ahead and take these values of the integers, one at a time, pi times 0 is 0, so we start at the origin. Pi times 1 is pi times 2 is 2 pi times -1 is -pi. So we've got an expression that works, right? Okay. Good. What is the y-intercept? Yeah, so it's just the origin, 0, 0. Okay, there's only the one y-intercept for the parent. Now, the maximum and minimum, just like the intercepts, we need to come up with an expression that's going to represent every one of those infinite points. We know the maximum itself is what? 1. Okay, so I'm going to say that occurs at, and let me go ahead and write this out as an ordered pair, because it is a location. Now remember, in the ordered pair, the maximum or minimum is the y value. The x just tells you where that occurs. So let's take a look at the graph again. All right. We got this guy right here. Now, let's think, if this pattern were to continue, this would be the next maximum I'd be at, right? So what's the period of sine? Remember, it's 2 pi. He repeats himself every 2 pi radians, every 1 revolution. So if I'm not going to see another maximum, again, for 2 pi radians, where would the next one occur? I'd take the first one, pi over 2, and do what? Times it? Plus it. You'd want to add it. There we go. So this one would be pi over 2 plus 2 pi. And actually, this is the one you looked at today on your happy minutes. The next maximum would occur at 5 pi over 2. So where would the next one be? I would take 5 pi over 2 and do what? Add another 2 pi. Then for the next maximum, I'd add another 2 pi. And now if I wanted to go in the other direction, I would subtract 2 pi. So how does this help me come up with an expression that I could use to help me find any of those? What am I going to multiply by the n that Aiden gave me? Okay, Dylan said it. 2 pi. So I'd go ahead and say pi over 2. This is the first one we have in that original cycle, plus 2 pi n. Again, where n is belonging to the integers. So you're just adding or subtracting multiples of 2 pi. Okay. Now let's see if you can come up with a similar expression for the minimum values. Again, you're going to have an infinite number of these. Okay, so I'll give you, let's say 15 seconds. Okay, so I'm going to go ahead and write it out the same way. We have a minimum -1 at, okay. So in the ordered pair, again, the y value is my minimum. So what expression should I write here to find any of those minimum locations? Dylan says 3 pi over 2 plus 2 pi n. That is exactly right. Because if you're looking over here at the graph, 3 pi over 2 is where the first minimum occurs of that period we're looking at. Okay. And again, you're not going to see the next minimum until another 2 pi radians down the line, and then another, and then another. Okay. Well, let's look at some other characteristics here. Is it continuous? Okay. Some people are shaking their heads yes. Okay. What was the basic definition of continuity if we're not worried about limits? I can draw it without doing what? Picking up my pencil off the paper. So absolutely, I can sit here and draw, there's one cycle, a second, a third, a fourth. I could just sit there and draw that as long as I wanted to. So it definitely is continuous. Is it bounded above? What do you guys think, yes or no? Okay, yes, because it has a maximum, right? It doesn't go to infinity, so he is bounded above. Is he bounded below? Yes, his minimum would be -1, as we've seen. Now, let's talk about symmetry. It's been a while since we've seen this. What does it mean if you have an even function? Say it again, Aiden. That's exactly right. If you are able to fold the graph along the y-axis, imagine that was your line of symmetry, then it's going to be an even function. So let's come over here to sine. Let me go ahead and draw the other portion of this to kind of help you out. If I were to fold along the y-axis, would these two parts come together perfectly? No, they're not going to do that. Okay, so this guy is definitely not even. And what does it mean if I have odd symmetry? Across the origin? There you go, that's what I'm looking for. You can rotate it. Okay. So imagine that I have my pivot point right here at the origin, and this is like a giant fan blade. If I can rotate it 180 degrees, just half a revolution, and end up with the exact same graph, then it's going to be an odd function. What do you think about sine? Could I rotate it 180 degrees and get the same graph? Yeah, absolutely. In fact, this minimum right here would become this maximum and vice versa. Yeah, you would get the exact same graph. So sine is odd. Okay. This means we have, or symmetric with respect to the origin. Okay. And then we have our key points. Remember, we started with a 0. We went from 0 to a maximum to a 0 to a minimum to a 0. We want to be really familiar with these key points. So we started at the origin. That was our first 0. What was the location of our first maximum? Remember, it was pi over 2, 1. Then our next 0. Then pi, 0. And then minimum. 3 pi over 2, negative 1. And we finish the cycle, get back around to 0. 2 pi. There we go. We definitely want to be very, very familiar with those 5 points. And really, for any period of sine, okay, you'll always be able to break it up according to these. Remember, the horizontal distance between these key points is always going to be the same. So you can always break a period up into fourths according to these. Okay. Well, now let's go ahead and do the same thing for cosine. But instead of my just giving you the graph like I did for sine, you guys are going to help me and tell me exactly what points are going to make cosine. Now, since the graph will complete one full cycle in the interval of 0 to 2 pi, the period of y equals cosine of x is 2 pi. Well, it's the exact same idea why sine is periodic for 2 pi radians. After you complete one revolution, what happens? All those values start to repeat, so I'm going to get the same graph over and over and over again. Okay. So coming over here, if you have a unit circle handy, okay, or if you just remember it off the top of your head, that's fantastic. But we're going to go ahead and run through the same values that we did for sine. Okay, so we're going to go ahead and generate our ordered pairs. Let's start with the cosine of 0 radians. Now remember, sine, you wanted what? You wanted the y value. But for cosine, you want the x value. So at 0 radians, yeah, the x value is 1. Okay, we're just going to work our way around the unit circle. So cosine of 0 is 1. Now this tells me I have what ordered pair? 0, 1. So cosine, its parent, he does not go through the origin. We're going to start off with a maximum. Okay, and now let's just go through those increments. Let's go to pi over 2. Cosine of pi over 2. Susie, what's cosine of pi over 2? On the unit circle, the x value. So on the unit circle, at pi over 2, what's cosine, the x value? 0. Okay. So that would be 0. So that would give me the ordered pair pi over 2, 0. So pi over 2, 0. That's my first x-intercept. Okay. And let's keep going. Next up is pi. So cosine of pi, let's go to Ariana. What's cosine of pi? Go back to the unit circle, okay. Cosine of pi. She says negative 1. That is absolutely right. So this gives me an ordered pair, pi, negative 1. So we know the first location of our minimum. Okay. Now let's go 3 pi over 2. All right, let's see. Bethany, help me out with this one. Okay, it is 0. That is absolutely right. So that ordered pair should be 3 pi over 2, 0. Okay. Oh, forgot to put the other one. So pi negative 1. 3 pi over 2, 0. And let's go ahead and finish up this last one. I'm going to go ahead and put it up here so I can draw the graph. So cosine of 2 pi. Okay. Christian, what do you think? Yeah, because this is where it starts to repeat. So cosine of 2 pi should be the exact same as the cosine of 0 because they're, what's the word I'm looking for? Coterminal. Okay. So this is 1, which gives me the ordered pair 2 pi 0. Whoop. I don't know why I put 1 there. Wait. Yes. It's a Monday. All right, 2 pi 1. Now for me, it kind of looks like cosine, the period that repeats the cycle is just like a curvy V. So it's going to kind of look like this. That's what's going to repeat for cosine over and over and over again. So in the next 2 pi radians, I would go down, come right back up. Go down, come right back up. And I'm going to be able to go in the other direction. This is if I were to rotate counterclockwise. If I wanted to rotate clockwise, then it would just go in the opposite direction. And it would just keep going. Okay. So is this starting to make sense where these graphs are coming from? Is everybody okay with these? Any questions? Now, while sine started with intercept, maximum, intercept, minimum, intercept, what do we do for cosine? He starts with a maximum, then goes to an intercept. And I'll just go ahead and put 0. Then we have a minimum, then we have another 0, then we're going to have our maximum to finish up. Now, just like sine, these 5 key points we want to be very familiar with. The distance between them horizontally, again, is going to be congruent. This little distance here compared to this one, and then this one. Just like sine, using these critical points, you're going to be able to take cosine and divide it up into 4 parts, 4 congruent segments. Okay. Again, that probably doesn't mean a whole lot today, but when we start looking at the transformations, that's going to be really, really useful to you. It's going to make things so much easier. Okay. So any questions? All right, well, I'll tell you what, that is as far as first and second period got. So we will go ahead and stop there. Tomorrow we'll come on in. We'll talk about the characteristics of cosine, and then we'll start talking about all the little pieces that go along with this. Amplitude and frequency, and phase shift, all that good stuff. Okay, good. All right, let's go ahead and get those calculators back on the wall, please. Or, but not on the wall, I mean on their charging station. Oh, I said the wall. Okay.